The speed of light is the fastest speed in nature. In a vacuum, it travels at about 300.000 kilometers per second. On Earth, that speed feels astonishing. Light can circle the Earth 7.5 times in a single second. It takes only 1.28 seconds to travel from Earth to the Moon. Here, light seems almost instantaneous. But when we shift our view beyond Earth, toward the solar system, the Milky Way, other galaxies, and finally the observable universe, the fastest speed in nature begins to look surprisingly slow. To understand this contrast, let us gradually expand our scale and watch how light changes from lightning fast to almost sluggish. We begin with the Sun. The average distance between the Sun and Earth is about 150 million kilometers. At 300.000 kilometers per second, sunlight takes roughly 8 minutes and 20 seconds to reach Earth. This means the Sun we see right now is actually the Sun from over 8 minutes ago. If the Sun were to suddenly disappear at this very moment, Earth would not fall into darkness immediately. We would continue to receive sunlight for at least 8 more minutes. Now let us move outward. The average distance between Earth and Jupiter is about 780 million kilometers. A beam of light traveling from Earth to Jupiter would need around 43 minutes to arrive. Pluto lies much farther away, at an average distance of about 5.9 billion kilometers. Light requires approximately 5.5 hours to reach it. Within the solar system, light has already transformed from instant to minutes and even hours. But once we leave the solar system and enter the Milky Way, the scale becomes staggering. The Milky Way is a flattened spiral galaxy with a diameter of about 160.000 light-years and a thickness of roughly 3.000 light-years. This means that light would need about 160.000 years to travel from one side of the galaxy to the other. Our Sun is located about 26.000 light-years from the galactic center. If an advanced civilization existed at the center of the Milky Way and sent a signal toward Earth, it would take 26.000 years to reach us. If we immediately replied, they would need to wait another 26.000 years to receive our response. A single conversation would take 52.000 years. At this scale, the speed of light feels painfully slow. Now we move beyond our galaxy. The nearest large external galaxy is Andromeda, located about 2.54 million light-years away. Light from Andromeda takes 2.54 million years to reach Earth. That means the Andromeda galaxy we observe today is actually what it looked like 2.54 million years ago. If intelligent life evolved there at the same time as on Earth, what we see now might only be their earliest stages of development. And what they see of us would be ancient human ancestors just beginning to walk upright. Finally, let us expand our view to the entire observable universe. The observable universe has a diameter of about 93 billion light-years. This limit exists because light has had only a finite amount of time to travel since the beginning of cosmic expansion. Beyond that boundary, light from distant objects has not yet reached Earth. As a result, everything beyond 93 billion light-years remains invisible to us. Even within this observable range, if a beam of light were to travel from one edge of the observable universe to the other, it would require 93 billion years. On the largest cosmic scales, even light appears powerless. Because of this finite speed, the universe we observe is essentially a historical documentary. Light allows us to see the past, but never the present moment of distant objects. This limitation also affects our dream of interstellar travel. Even if we could travel at the speed of light, crossing the galaxy would still require tens of thousands of years. However, Einstein's theory of relativity tells us that no object with rest mass can actually reach the speed of light. As an object approaches light speed, its mass increases due to relativistic effects. To push it all the way to light speed would require infinite energy. And infinite energy does not exist. Therefore, the speed of light is the ultimate speed limit of the universe. Unless we abandon the idea of speed altogether, concepts such as warp drives and wormholes attempt something different. Instead of accelerating an object faster, they propose bending spacetime itself. General relativity tells us that spacetime can be curved, and the greater the mass, the stronger the curvature. Warp drives imagine expanding spacetime behind a spacecraft and contracting it in front, effectively shortening the distance. Wormholes suggest folding spacetime so that two distant regions become directly connected. However, these ideas remain purely theoretical. Although we know spacetime can curve, we still do not know how to manipulate it at will. In the end, the speed of light is both extraordinary and humbling. On Earth, it feels instantaneous. Across the universe, it reveals how vast reality truly is. Even the fastest thing in nature cannot outrun the scale of the cosmos.